Good evening, everyone. Welcome to the fifth live interactive session of Symmetry and Group Theory. In the last session, we discussed about the properties of group and how these properties are helpful in understanding group multiplication table, and also we learned how to classify different symmetry elements into classes in a group. So we took different examples of the point groups and classified different symmetry elements in classes, following certain rules and patterns. So we solved a lot of examples, and today we will be discussing about the representation for group. So let's begin our fifth session. Representations for group. So we will be discussing about the metrics. Firstly, we will be discussing the matrix representation of symmetry elements. Like what will be the matrix representation of C2G, sigma XY, sigma YZ, inversion, symmetry element, and an improper axis of rotation. Okay. So first is matrix representation of symmetry elements. So firstly, let us make a three coordinate system. We represent this axis as g-axis, this is y-axis, and this is x-axis. So if we apply a C2G operation on this three coordinate system, so what will be the changes, what will be the configuration we will observe in this system? So this is the C2G, we will be applying C2G along this, and so the position of g-axis will not change. However, y-axis and and x-axis will change their positions, like they will go in opposite directions. So if I say the matrix representation for this XYG system undergoes a C2G operation, so the changes we have observed are x changes to minus x, y changes to minus y, and g remains same. So this is how we will be finding out the metric representation of symmetry elements. So let us see. If we represent them as minus x minus y g x y and g. So here, if we multiply this, considering this the magnitude, so what will be the output? So here we will get minus one, because following this metric system, this is the metric system we will get. So the matrix for C2 will be minus 1, 0, 0, 0, minus 1, 0, 0, 0, 1. So if we find out the character of this C2 matrix, which is the sum of matrix elements along diagonal. So this is what we call character of a matrix, which we are representing as this. So minus 1 plus minus 1 plus 1. So what will be the character of this matrix of CO2 of C2? It will be minus 1. So the character for C2 is minus 1. Now if we find out the matrix for sigma xd, so this is a three coordinate system, and if we apply the operation sigma xd on this system, so what will we get? This is the plane we are following, the operation that sigma xt is being applied here. Okay, so this g axis and x axis will remain same. There will be no changes in these axes. However, we will observe a change in y-axis. That is, we will find a reflection of this y-axis in the opposite direction. And this will be represented as, so these xyz coordinates on undergoing this sigma xt operation, they will change, they will give this x minus yg coordinates. So the coordinate system for this metric system for this sigma xy will be is 1 0 0 0 minus 1 0 0 0 and 1. So what will be the character for this matrix? Again, we will sum up the matrix elements along diagonal. So the character of this matrix will be 1. Okay. Similarly, if we find out it for sigma yg, I'm taking it directly now. Xyg undergoes sigma yg operation, then y and g will remain same, and the coordinates of x will change, that it will be reflected in the opposite direction. So we will get minus x, and the matrix for sigma yg will become minus 1 0 0 0 1 0 0 0 1, and the character of this matrix will be 1. So this is character of the matrix. It will be very helpful for you in making group multiplication tables for different point groups. So please understand it very carefully. And if we apply identity operation on this xyz coordinate, what will we get? We won't get any changes because this is unity operation. So there will be no changes, And the matrix representation of this symmetry of identity element is, we will get 1 0 0 0 1 0 and 0 0 1. And again, the character of this matrix will be 3, as you will sum up the matrix elements along this diagonal. Okay, now the character for inversion element. So if we apply the inversion operation like on the origin, so we know all of them will be reflected in the opposite direction, and we will get, so the matrix elements for this inversion element is this. So what will be the character for this? It will be -3. You will have to remember these characters, okay? So now I'm listing out the character for each of the symmetry elements in this table. Please follow it to solve any kind of examples you will be doing in the practice sessions or anything. Okay. Here I'm writing the symmetry operation, and this is the character of that particular symmetry operation. So first is C2. We have already found out that the character for C2 will be -1. Okay. For C2 it is -1. For sigma xg it is 1. For sigma yg it is 1. So for any kind of reflection, like any kind of the like the sigma plane, you will always get this character equal to 1. So I'm writing it here. For any kind of sigma, the character will be 1. And for E, we have found out that for identity element, it was 3. For inversion center, which is also equal to S2, it is equal to -3. And C3 axis of rotation, here you will be following that trigonometric type of metric system. So you will get 0 as the character, and for C4 you will get 1. Then for S3 it will be -2. For S4 it will be 1. And you can also find out these characters by basically writing the metric system of each of the symmetry element. Okay. So I'm just writing here a general matrix of C and axis. Matrix 4 of n-fold axis of symmetry. So Cn is equal to cos theta sin theta. So it will be basically Cng, because I'm saying it Cng because for the principal axis, wherever whatever will be the direction of this principal axis of rotation, you will be taking g-axis along it. Cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. And what will be the character? It will be sum of the diagonal elements, which is 2 cos theta plus 1. For example, we took this C. For example, we took this C3 axis. So for C3 axis, we will be taking cos 120, which will be giving us this C3 minus 1 by 2 plus 1. So as we have mentioned in the above table, it is 0. So you can directly find out the character of a particular matrix system. So I'm writing the examples over here for C2 axis. Theta is 180 degree. So the matrix for the C2 axis will be minus 1, 0, 0, 0 minus 1, 0 and 0, 0, 1. Since cos 180 is minus 1 and sin 180 is 0. And you can directly put these values in this general metric system I have mentioned here. Okay. So the character for this will be sum of the diagonal elements, which is minus 1. For C3, I have solved it over here. And for C4 axis of rotation, which is theta is 90 degree, so the metric system will be 0, 1, 0, minus 1, 0. So whatever the elements are present in the metric system, we will have to sum up only the elements along the diagonal. So for this matrix, the character will be 1. So I would suggest you remember, you understand these metric systems and remember these characters for all of the symmetry elements. Okay. So now we will be discussing metrics for S and G axis. So this S and G is multiplication of the CNG symmetry operation and a plane perpendicular to it, which is sigma xy. So the general metric system for this SNG will be cos theta, sin theta, 0, So for Sn, this will become minus 1. You might remember that in the Cn it was 1. So this is the only difference here. Okay. And now you can directly find out this character for any kind of, like, it can be S2, S3, S4, whatever you want to solve. So let us take a few examples. For S2, it is multiplication of twofold axis of rotation and sigma xy. So it will be minus 1, 0, 0, 0, minus 1, 0, and 0, 0, minus 1. So if you see here, like for the C2, it was same up till now, and here it was 1. So in this case, the only difference is over here. So the character will be minus 3. As for improper axis, fourfold improper axis of rotation, minus 1 by 2, 0, 0, minus 1. So these characters of matrix for symmetry elements will be utilized as contribution per atom for derivation of reducible representations. So what are the reducible representations for molecule? So a representation of higher dimension, which can be reduced further to the representation of lower dimension, is what we call reducible representation. So I'm writing the definition here. A representation of higher dimension which can be reduced further to representations of lower dimensions. So we can find out the reducible representation of a molecule uh, after selection of appropriate basis of sets, which has been already explained in the main lectures by professor. So here I am writing what are the basis sets we generally follow. A reducible representation for a molecule after selection of appropriate basis sets. So there are like five different type of basis sets which are applicable for the derivation of reducible representations. So these are first is three axis system for which we have already found out the matrix systems. Second is 3n coordinates. So 3n coordinates here means like all of the atoms present in the molecule. Coordinate system for each of the atom is specified in this basis set. So n is number of atoms in molecule. Third is number of unshifted atoms. Fourth is bond vectors. That is bond between two atoms. So we consider them as vectors. And fifth is bond angles, angle between the atoms. So now we will be taking an example, which is like water, S2O, and we will be finding out the reducible representation for each of these basis sets. And this will help in find like follow a pattern to how can we find out the reducible representations for a particular molecule. So firstly, we will find the basis set for. So here we will find the reducible representation for which the basis set is three coordinate system. So, so these metric systems we found out about like these were for three coordinate system only. So these character table, these symmetry elements I have written in the character table. These are for three coordinate systems. So we can directly write the reducible representation with respect to each of these symmetry elements. So C2V has what are the classes in C2V point group? It is identity element, then twofold axis of rotation, sigma xg plane and sigma yz plane. So for E, we have already found out that the character for E is 3. For C2, it was -1. And for any kind of sigma plane, it is always 1. So this is the three-dimensional representation for water. So this value below this identity element, it shows the dimension of the system. Like this is three-dimensional reducible representation for water. So now if we find out the reducible representation for which the basis set is unshifted atoms. So when we apply these symmetry operations with respect to a particular group, like here we are having S2O comes under this C2V point group, which has these operations, identity elements C2X, sigma Xc and sigma Yc. So when we apply these operations on this water molecule, so what are the unshifted atoms uh, during each of the operation? It will give the reducible representation for what for that molecule. So here we have C2V point group and the classes are E, C2, sigma X, sigma YZ. So first is identity element. So we know when we apply this identity operation, there are no changes. We don't observe any changes in the system. So three atoms, that is water, this one, two, three, this oxygen atom and these two hydrogen atoms will remain unchanged. So we will have reducible representation for it as 3. For C2 axis, so C2 axis will be along this direction. This is C2G axis. So when we apply this operation, these hydrogen atoms will change their position. So only one atom is remaining unchanged during this operation, which is oxygen atom. So it will become 1 here. And if we apply sigma xg is molecular plane. So in this molecular plane, there are no changes in the whole molecular system. So it will give 3 as the reducible representation. And for sigma yg, which is along the C2G axis, so when we apply this operation, these two hydrogen atoms will reflect and will exchange their positions. And the only atom which is remaining unchanged over here is again oxygen atom. So we will have one unshifted atom here. So this is the three-dimensional representation for water based on the unshifted atom basis set. Since here again we have this 3 under identity element. So this is the dimensional reducible representation for water. So now we will find out the reducible representation for water under the basis set 3 and coordinates, where we will be considering the coordinate system along each of the atom. The basis set is Here we will have z axis. So labeling each of the atom, this is 1, this is 2, and this is 3. So this is z2 axis. So this is x2, and this is y2. For this is z1, y1, and x1. So here we have taken coordinates for each of the atom. Now if we write the matrix for this identity element for each of the atom, how will it look? For each of the atom, we have this x, y, g coordinates: x1, y1, g1, x2, y2, g2, x3, y3. So the coordinate for each of the atom will be this. So I'm writing it as whole 0 over here, and for the x2 this oxygen atom, it will be 1, 0, 0, 1, 0. So again, if we find out the character for this metric system, it will be along diagonal for the complete metric system. So sum of the symmetry of the elements along the diagonal is 9. So the character will be 9. And if we apply the C2 operation, y2 g2 x3 y3. So we are applying this C2 operation. So when you are applying the C2 operation over here, so this H1 atom is being replaced by this S3 atom. That is, the position of H1 and S3 are being exchanged. So uh, in in the place of G1, it will become G3. In place of Y1, it will become Y3, and with the opposite signs. And in the place of X1, it will become minus X3. And in the coordinates of oxygen, x2 will become minus x2 and y2 will become minus y2, and this g2 will remain as it is. So this is very simple, but let me write it here. Since the positions are being exchanged along with the direction change of these coordinates, so it will become x1 will become minus x3, y1 will change to minus y3, G1 to G3, x2 will become minus x2 because its position is not changing, but the direction of these x's will be changing. So minus y2, G2 will become x1 minus y1 and minus g1. The coordinate for these changes will be, uh, I'm writing it here. If you see, since we are having x3 y3 over here, so it will become minus 1 0 0 0 minus 1 0 0 0 1. Similarly here, so if you take the sum of characters of, sorry, elements along the diagonal, it will be minus 1. So if we write the reducible representation for this whole system, so there is this rule that reducible representation for 3n coordinates, like for n number of atoms and the coordinates with respect to each atom, it will be multiplication of reducible representation basis set with respect to unshifted atoms into contribution per atom, which we have found from this XYG system. Okay, so if I write it here, E C2 sigma XY sigma YG. So the basis set with respect to unshifted atoms, it was 3131. 3131. And for three coordinates, what are the characters we got? With respect to identity, it was 3. With respect to C2, it was minus 1. And for any kind of sigma, it is always 1. So if we multiply these reducible representations for unshifted atoms and three coordinates, we will get reducible representation for 3n, which is 9, 1, minus 1, 9 minus 1, 3, 1. Okay. So let us take another example, BF3. Just a minute. So we will be finding out the reducible representation directly following this equation. So BF3 is C3V point group. Mm, What are the classes, symmetry operations, and what are the classes for C3V? E, 2C3, 3C2, sigma H, and 3 sigma V. I hope you have learned now like how to find the point group of a particular molecule and write these symmetry operations and classifying all the symmetry elements in particular classes. So the unshifted atoms. So the number of atoms over here are 4. P, F, F, and BF. So under identity operation, all the elements will remain, all the atoms will remain same. So it will be 4. And if we apply this C3 axis of rotation, which will be in the middle and coming out of the plane. So these three fluorine atoms will change their positions. Only this boron atom will remain unchanged. So here we will have one atom. And if we apply this 3C2 axis, which will be along each of the BF bond. So uh, two of the fluorine atoms will change their positions, and this BF boron and one of the fluorine atom will remain unchanged. So the number of unshifted atoms will be 2. And then sigma H plane, which is the molecular plane of the system of this, which is like the board plane of the board. So all of the atoms will remain unchanged, and again we will get character as 4. And for S3, which is like C3 axis of rotation followed by a sigma H reflection, that is sigma XY, which is the molecular plane over here. So we will get only one atom unchanged during the whole operation, which is boron atom. So it will be 1. And for sigma V, which will be again along one of the BF bonds, so only two atoms B and F will remain unchanged. So it will be 2. Now contribution per atom, which we have already written above. For with respect to x, y, g coordinates, we have found out the matrix for each of the symmetry elements and the character of each matrix. For E, it was 3. For C3, 0. For C2, it was minus 1. For any kind of plane, it is 1. Then for S3, it was minus 2. In sigma V, it is 1. So the reducible representation for 3n will be multiplication of reducible representation with respect to unshifted atom basis set and contribution per atom basis set. So it will be 12, 0, minus, minus 2, 4, minus 2, and 2. Okay. So let us take a few more examples where we'll be finding out the reducible representation for each of the basis set. Next is CH4. So CH4 comes under tetrahedral point group. The symmetry operations in this tetrahedral group classified into classes are E8C3, 3C2, 6S4, 6 sigma D. So reducible representation for three coordinates. For E it is 3, for C3 it was 0, C2 it is -1, for S4 it is -1, and for sigma it is 1. And reducible representation for unshifted atoms. So during the identity operation, all 5 atoms will remain unchanged. And for C3 axis of rotation, 2 atoms, because this C3 axis will be along this direction. So 2 atoms will remain unchanged. For C2 axis, which will be passing between these atoms, so only 1 atom will remain unchanged. Then S4 axis of rotation, only 1 atom, which is carbon atom, will remain unchanged. And for sigma planes, which will be if we which will be taking two planes, two bonds, two CH bonds along it, and one hydrogen atom out of plane, and one like towards the observer, and one um, away from the observer. So in this case, 3 atoms will remain unchanged. So reducible representation for 3n will be multiplication of these two reducible representations, which is 15, 0, -1, -1, and 3. Now reducible representation bond vector. So each of the bonds will be considered now bond vectors. Like each of the CH bonds will be a bond vector. So when we apply each of the operation, so which how many number of bonds are remaining unchanged, that we will have to find out. So there are 4 bonds, 4 CH bonds. So each of these will remain unchanged during this identity operation. And in the C3 axis of rotation, only one CH will remain unchanged. And this 3C2, when we will apply, none of the bond will remain unchanged. So it will be 0. And for S4 also, it will be 0. For sigma D, because it will be taking 2 bonds, 2 CH bonds on it. So these 2 bonds will remain unchanged. So it will be 2. So there's a small trick here which I'm writing. So you can directly found out this reducible representation for bond vector by applying this thing, that is unshifted atom -1. So you just have to subtract 1 from the uh, unshifted atom, which is like 3 here. Sorry, here, 5 here. So 5 minus 1 it will become 4, 2 minus 1 1, 1 minus 1 0, 1 minus 1 0, 3 minus 1 2. So you can directly found out the reducible bond vector. Now reducible representation for bond angle. So the cases where the bond angles, like the number of atoms are lesser, and there you can easily found out the reducible representation for bond angles. But uh, with as the number of atoms increases, it becomes difficult to find out the changes in the bond angles and the possible bond angles in the molecule. So generally, this is not asked generally, but you should know how to find it out. So for CH4, I'm representing it as like this. One hydrogen atom, which is above, where we have the C3 axis of rotation along with. So I'm writing it as this H1, H2, and H3. So we have like bond angle between each of these atoms, which is theta 1 3, theta 1 2, theta 2 3, and each of the atoms have a bond angle with a hy- this fourth hydrogen atom. So it will be theta 3 4, theta 1 4, and theta 2 4. So now if we apply these operations, so how many angles we have? We have six angles. So in the identity operation, these six angles will remain unchanged. And when we apply this C3 axis of rotation, only no bond angle will remain unchanged because all of these atoms will be changing their position. So bond angles will be changing. So it will be 0. And for C2, it is 2. But as for it is 0. So sigma, it is 2. Similarly, if we take an example of D3H point group, which is like PCl5 trigonal bipyramidal molecule, a molecule with trigonal bipyramidal geometry, PCl5. PCl, PCl. So if you write the symmetry operations in the D3H point group, it is E2C3, 3C2, sigma H, 3S3, and 3 sigma 4. So reducible representation for 3 coordinate, it is 3, 0, minus 1, 1, minus 2, and 1. reducible representation for unshifted atoms. So the number of atoms here are 6. So under identity operation, no atom will 6 of the atoms will remain unchanged. So along C3, which will be along this axis, so the Cl, PCl will remain unchanged. So we will write 3 atoms remain unchanged. And when we apply the C2 axis, two atoms will remain unchanged. So you will learn this how to find all of these with practice. So practice as number of molecules as you can. And then for sigma H, which will contain this Cl bond, this phosphorus atom, this Cl atom on it. So these 4 atoms will remain unchanged. And for S3, only 1 atom will remain unchanged, which is phosphorus. For sigma V, I have written it sigma 4. It is sigma V. So again, for it, uh, 4 atoms will remain unchanged. So the reducible representation for 3n will be multiplication of about 2 representation, which is 6 3 are 18, 0, minus 2, 4, minus 2, 4. Reducible representation for bond vector, it will be just we have to subtract 1 from the unshifted atom. So it will become 5, 2, 1, 3, 0, 3. So reducible representation for bond angle. So here we have like how many angles we have? 10. So you will have to figure out how these angles are changing. So I'm writing it here directly. 10, 1, 2, 4, 1, 4. So these are the reducible representation with respect to the 5 basis sets we have mentioned above. Okay. A few more examples I'm writing. So I would like to request if you are following these interactive sessions, like you are following the recorded sessions on the YouTube, I would request you to join these sessions because it becomes helpful for me. I will get to know like in which where are you facing problems and what kind of problems I should solve and what content you want to learn. So it will be helpful for me also, and I will be happy to know your feedback and any suggestions you can give to improve these sessions. So try to join these sessions as much as possible, and you can post any of your doubts and we can further solve these doubts in the sessions. So these sessions are meant to help you only, and if you are not going to join these sessions, so it becomes difficult for me to choose the content you want to like you are facing doubting. So I'm just taking content like I'm using the similar content with respect to lectures and trying to solve the problems which can be helpful for you in solving the assignment problems. Okay, so please try to join these sessions. It will be really helpful for you and for me also. Thank you. So next is this. So the point group for this molecule is, firstly we can see a C2 axis of rotation as the principal axis. Then we have sigma V plane also along the C2 axis, and one is the molecular plane. So this is C2V point group. E C2 sigma xg sigma yg. So reducible representation for three coordinates, it will be 3 minus 1 1 1. Reducible representation for unshifted atoms. So number of atoms over here are 1 2 3 4 5 6 7 8 9 10. So we have 10 atoms. When we are applying the C2 axis, there are no atom which is which is remaining unchanged. So it will be 0. And when we apply the sigma xt, which is the molecular plane, so all of the atoms remain unchanged. So it will become 10. And when we are applying sigma yz, again it is 0. So the reducible representation for 3n will be 30, 0, 10, 0. So this will be mainly be used in the applications of these group tables in the coming lectures. So it will be very helpful for you. So please try to solve maximum examples. And the next is pyridine. Sigma yg. So this is your task to find out how C2V, how this molecule has C2V point group. Okay, so the reducible representation for the three coordinates will be 3 minus 1 1 1. Reducible representation for unshifted atoms. So the number of atoms here are 1 2 3 4 5 6 and 7 8 9 10 11. So we have 11 atoms. When we are applying the C2 axis, so 2 atoms are remaining unchanged. Sorry, 3, because we have these hydrogen atoms also. So the sigma xt, which is the molecular plane, all of these atoms will remain unchanged. For sigma yz, again it will be 3. See how easy it becomes to find out these reducible representations this way. It will be 33 minus 3, 11 and 3. So another example is this trans butane 1,3-diene. Above this was cis but 1 cis but 1,3-diene, and this one is trans. See see how different isomers, configurational isomers give you different point groups. So what is the point group for this molecule? It is C2H point group. So you will be specifying each of the symmetry element in it. Bit 10, 0, 0, 10. Unshifted atom. Sorry, this was for unshifted atom. This is for the three coordinates. Reducible representation for 3n will be 30, 0, 0, and 30. Sorry. We take another example, Genan F4, which has square pyramidal geometry. With if you take a MX4 type of molecule with square pyramidal geometry, so it has C4B point group. The symmetry operations in it are 2C4, C2, 2 sigma V, and 2 sigma D. So if we find out the reducible representation for unshifted atoms, will be 5, 1, for C2 again 1, sigma V 1, and sigma D 3. And for 3 coordinates will be 3. C4 give us for C4 it is 1. is 1, C2 minus 1, and for any kind of sigma is 1. So reducible representation for 3n will be 15, 1, minus 1, 1, 3. So we will be taking a 5-minute break. Uh, Now we will be discussing irreducible representation for groups. Presentations for groups. So what is an irreducible representation? So when a representation of lower dimension which cannot be reduced further is what we call irreducible representation. So it is a property of point group, and irreducible representation for a group can be derived using postulates of great orthogonality theorem, which we'll be discussing. So I'm writing the definition here. A representation of lower dimension which cannot be reduced further is known as irreducible representation. Can be derived using postulates of great orthogonality theorem. So there are four postulates of great orthogonality theorem. So I will be deriving the irreducible representation for C2V point group following these four postulates. So we are taking the example of C2V point group. Okay. So first postulate is derivation for C2V point group. So the first postulate is number of irreducible representation for a group will be equal to the number of classes in the group. So the number of irreducible representations that can be found in a group will be always equal to the number of classes in the group. So for a group will be equal to the number of classes in the group. So for C2A point group, how many classes do we have? We have identity element, then C2 axis, then sigma xg and sigma yg. Each of them are in different classes. So there are four classes. So here the order is 4 and the number of classes also 4. So the irreducible representation will also be equal to number of irreducible representation will be equal to number of class is equal to 4. So we will have four classes R1, R2, R3 and four reducible representations R1, R2, R3 and R4. So what will be the elements in this group? Let let it is K1, K2, K3, K4, L1, L2, L3, L4, M1, M2, M3, M4, N1, N2, N3, N4. So this is the first postulate to create uh, to create a group for the particular point group table for a particular point group. And the second postulate is sum of sum of square of dimensions of irreducible representation for the group will be always equal to the order of the group. That is sum of squares of dimensions of what are the dimensions? So the values below this identity element in each of the reducible representation will be the dimension of that group. Sum of square of dimensions of irreducible representations for the group will be equal to the order of the group. So it will become K1 square plus L1 square plus M1 square plus N1 square is equal to 4 because the order of the C2B point group is 4. So what could be the possible dimensions which can give this value equal to 4? So it can be 1 square plus 1 square plus 1 square. So each of the reducible representation has dimension of 1. So it will give 4. So the point group will become this group multiplication table will be E C2 sigma xg sigma yg R1 R2 R3 R4. So it will become 1 1 1. So N2 N3 and N4. So the next postulate is, so the third postulate is sum of square of characters for irreducible representation will be equal to the order. So each of the sum of square of each of the character in an irreducible representation will be equal to the order of that particular point group. Sum of square of character for irreducible representation will be equal to the order of the point group. So if we take first irreducible representation R1, so it will be 1 square plus K2 square plus K3 square plus K4 square. So it will be equal to 4. So what could be the possible values of K2, K3 and K4 such that this sum of squares of these characters will become 4. So it can be 1 square plus 1 square plus 1 square plus 1 square is equal to 4. So, so now the group multiplication table will look like this. So the fourth postulate, which is very important to create a group multiplication table of a point group is, so it says that any two irreducible representation of a group will be orthogonal to each other. So what is this orthogonality theorem? That is R1 into R2 is equal to 0. So if we take any of the irreducible representation in any of the two irreducible representation of a group, then the sum of products of the character of these two irreducible representation will be 0. So any two irreducible representations will be orthogonal to each other. So With the help of this fourth postulate, we solved the group multiplication table, which will now look like this. R1, R2, 3, R4. So 1, 1, 1. So now we will have to put the values of these characters such that the multiplication of these representations, any of the two representations, and the sum of these representations will be equal to 0. So if I put it -1, -1, 1, -1, 1, 1, -1, -1. So if you take any of the two representations here, you will find out that each of these irreducible representations are orthogonal to each other. So now we have understood these four postulates of the group orthogonality theorem. So now we will find out the group multiplication table for C3V point group. So firstly, you will find out a molecule which has C3V point group. Then you will be finding out the symmetry operations in that point group, and then you will be classifying them into different classes. So for C3V, it is E 2C3 and 3 sigma V. So here for C3V, order is 6 and the number of class is 3. So the number of irreducible representation will be 3. R1, R2 and R3. So since if we apply this first postulate such that uh, the square of dimensions of each of the irreducible representation is equal to order of the group, which is this second postulate. So if we put this value as K1, K2, K3, L1, L2, L3, N1, N2, N3. So following the first postulate, this K1 square plus L1 square plus N1 square should be equal to, must be equal to 6. So what could be the possible dimensions which give this equation equal to 6? So it can be 1 square plus 2 square plus 1 square. So the point group will become E2C3, 3 sigma V, R1. So I'm putting it like this. Any of them can be considered. K2, K3, L2, L3, N2, N3. Now, following the second postulate, that sum of square of characters of any irreducible representation must be equal to order of the group. This is the third postulate. So according to it, if we follow 1 square plus k2 square plus k3 square must be equal to 6. So now what can be the values we can put here? Again, the possible values are like this. Sorry, we will have to consider the number of atoms also. Will be 1 square plus 2 into k2 square plus 3 into k3 square. So this should be equal to 6. So then what can be the value of k2 and k3? It will be 1 only. 1 square plus 2 into 1 square plus 3 into 1 square is equal to 6. So now the group multiplication table will become, so following these step by step you can create group multiplication table for any point group. So R1 will be 1, 1 and 1. R2 and 3. So now we have L2, L3, M2 and M3. Now if we use fourth postulate, that is sum of any two representation must be equal to 0. So I am taking this R1 into R2. It will be 1 into 1 plus 2 into 1 into L2 plus 3 into 1 into L3. It has to be 0. So 1 plus 2L2 plus 3L3 is equal to 0. So now what can be the values of 2L2 plus 3L3 is equal to minus 1. So what could be the possible L2 and L3 values? So L2 should be 1 and L3 will be minus 1. Similarly, if you apply for R1 into R3 equal to 0. So it will be 1 into 1 plus 2 into 1 into 2 into M2 plus 3 into 1 into M3 equal to 0. So it will become 2M2 plus 3M3 is equal to minus 1. And similarly, if we take R2 into R3, we will get two equations. One into 1 plus 2 into 1 into m2 plus 3 into 1 into 3 into minus 1 into m3 equal to 0. So it will be 2m2 minus 3m3 is equal to minus 1. So solving these two equations, first and second, we will get 4m2 equal to minus 2. So m2 will be, sorry, here it will be 2. It will be minus 2. So m2 will be minus 1, m3 will be therefore 0. So what will be the group multiplication table now? It will be C3V E2C3 3 sigma V R1 R2 R3. So the group multiplication table will be 1 1 minus 1 2 minus 1 and 0. So based on these four postulates, direct questions are also asked in exams. For example, if it is given that that for a point group, if order is 10 and classes is 4, then what will be the dimension of that irreducible representation? For a point group, if order is 10 and the classes is 4. So there are 4 classes. So it will be, if I take a particular irreducible representation and take the square of that particular, take a, take sum of squares of characters of that particular irreducible representation, it will be equal to 10. So what could be the possible values? It will be 1, 1 plus 2 square plus 2 square is equal to 10. So this is how you can solve a number of examples, and let us take one more example, one more question. So evaluate the number of one, two, and three-dimensional irreducible representations for D3H point group. So firstly, you will be find out the number of operations, total number of operations, that is order of the group, which is equal to 4, and it will be 12, and the symmetry operations present. So write all the symmetry operations with respect to that point group. Then classify them into classes. Okay, so the number of classes we have are 6. So now we will be having 6 irreducible representations. So we will be taking the sum of characters under identity operation, which are basically the dimensions of each of the reducible representation, and we will be taking a sum of the square of those characters, and we will be checking like how many of them are one dimensional, two dimensional, and three dimensional. So here the number of class is 6 and order is 12. So it will become 1 square plus 1 square plus 1 square. So this you will have to choose arbitrarily but following all of the postulates. So this shows we have for one dimensional we have 3 irreducible representations. Sorry, 4 irreducible representations which are of one dimension, and there are of two irreducible representation with two dimension, and there are 0 irreducible representations which have three dimension. So these are some examples for today's session. I hope everything is clear to you. If you have any doubts, please write to me, or you can. I'm requesting you again. Please try to join these sessions. These are for your help only. So uh, this is uh, this is it for today. Thank you.